Okay, guys, where did we leave off? Question 10. The Census Bureau reports that 12% of the population is left-handed. You are interested in the statistics, so you sample 100 people and ask if they are left-handed or not. So right away, we can do some quick math to figure out if we have a normal distribution here. So we are going to look at, let me choose a different color. Is n times p greater than 10? So what you do is you multiply your n, which is 100, times your p, which is 0.12, and that is equal to 12, so that is true. Then you need to do n times 1 minus p, so that's 100 times 1 minus 0.12, and that I think is 0.88, or exactly 88, sorry, mental math problem here. And so is that greater than or equal to 10? Also true. So we in fact have a normal distribution here. Okay. Give the probability of observing 24 or more left-handed people out of the sample of 100. So our original P is 0.12, our N is 100, our X is 24. That means our P hat, or what we are trying to find out, is what is the probability of that 24 out of 100 people will be left-handed, and that ends up to be 0.24. That's what we're checking for. Our original probability, because it's a normal curve, is 0.12. Our sigma, our new standard deviation, follow the formula, blah, 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 is 0.0325. Now we can find our z-score because we have our observed, or what we want to observe, minus the mean divided by the standard deviation, and that z-score is 369. So this z-score is pretty high. So if we're trying to figure out the probability that it's going to be that high, I'm guessing at this point that it's going to be pretty low. If you remember from your empirical rule, only 0.025% of your data is going to be above 3 standard deviations. So 3.69 standard deviations is going to be even smaller than that. To find your exact answer, what is greater than that, go ahead and put it in your normal CDF. We want to find that area under the curve that is greater than 3.69. I think I had originally just accidentally written down 3.67, so you may get a different value here. Starting at 3.69, going to your top value being infinity, is going to be really, really, really close to 0. So 0.0001. All right, so same problem, different numbers and characteristics. The Census Bureau reports that 68% of the population owns a smartphone. You're interested in the statistics, so you sample 100 people and ask if they own a smartphone or not. Really quickly, let's decide if this is a normal curve. So we do 0.68 times 100, and that is greater than or equal to 10, true. And then 0.32, which is 1 minus 0.68 times 100, 32 is also greater than or equal to 10. So we do have a normal curve for our answer. So we can go ahead and do this problem. Same math. So find your sigma, find your p hat, and your mean. Okay, going through, we find our z-score to be negative 0.64. So this time, when you do your normal CDF, you want to find out the probability of observing less than 65. So what we need to do is, our lower bound of our normal CDF is going to be negative infinity. Then our z-score for 0.65 is going to be negative 0.64, and your probability 0.2610. Okay. All right, a confidence interval problem. Suppose you want to estimate the proportion of CCD students that drive to school. You decide to sample 175 students and find that 35 drive to school. So that's our p hat. Right here, our proportion is 0.2 of our sample. Construct a 90% confidence interval for the proportion of all CCD students that drive to school. Interpret the results. So we need to, using this 90%, if you can find that table from either, I can't remember if it was, which module it was when we were doing confidence levels, but it gave us the numbers to use for a margin of error based on our confidence interval. So because we have a confidence in question A of 90%, we are going to use this as your Z alpha, I think is what they called it. And then we are multiplying it by one of your sigmas, and we are going to get 0.0497. This is our margin of error. In order to find our lower bound and our upper bound, we are going to both subtract that from our p hat to find the lower bound and add it to our p hat to find the upper bound. So we find the margin of error, we subtract and we add it to our p hat. And you must interpret your result, and that's here in yellow. We are 90% confident that the percent or proportion of students that drive to school, of CCD students that drive to school, is between 15.03% and 24.97%. Okay, you are doing the same exact thing for B. I'm not going to go over the whole thing, but our margin of error uses the number 1.96 instead of 1.65 because we want to be 95% confident. Okay, so this number, your margin of error is going to go up, okay, which is going to give us a greater range. So we can be more confident, but what's happening is we're becoming less precise, right? We're making our range bigger. So interpreting this result would be we are 95% confident that the proportion of CCD students that drive to school is between 14.07% and 25.93%. Don't forget, you must interpret this result, even though I didn't write it down in your key. That's the interpretation of it. Now we're doing it again, but in this case, we have a 99% confidence level. So that's going to change our value here. Our Z of alpha divided by 2, I think is what it is, to be 2.576. The rest stays the same, but our margin of error is now higher, which is going to make our range larger and our answer less precise. So we are more confident, but our values are going to be less precise. So we are 99% confident that the percent of CCD students that drive to school is between 12.21% and 27.79%. So D, as I've been stating, as the confidence percent increases, the margin of error increases, and our answer is less precise because of it. Why can't I? Oh no! All right, I'm gonna pause this while I get, because we're almost done. I'm gonna pause this while I put this back together. All right, you guys, so our last, I think, 2 questions. And then we're done. Our last 2 questions are about our hypothesis testing. The first one is dealing with the mean. So what we do is we go through here and we pull out some information. Our mu is 16.1. Our N, 49 businesses are selected to do our testing and showed a mean of 15 employees. So our X bar is 15. And our sample standard deviation is 25, okay? So what it wants us to do, and it gives us our significance levels, which in your project, I just asked you to choose your own since it wasn't in there. Just make sure you state what it was. Provide a summary of your statistics, so we did that. And we just want to know if it is different from 16.1. So when we write our hypotheses, we'd say our null hypothesis is that mu is 16.1, or the mean is 16.1, versus our alternative hypothesis, which is the mu or the mean is not equal to 16.1. And we're going to test that based on this sample that we took. So in our sample, we find our standard deviation of our sample to be 25. which is the sample standard deviation divided by the square root of our sample size. So our sigma of our sample is 3.5714. Then we're going to perform the t-test, okay? And that is going to be, you put it in, and I think you can also do this on the calculator. I'm going to pause really quick and double check so that you don't have to watch me do it wrong if it is wrong, but I think you can. So hold on one second. All right, you guys, it looked like I was right. So you can either follow the steps that I just did and then find your t-score using this method here, okay? Or what you could do once you have your statistics, whoops, and this might be easier for you guys, is you go stat, test, t-test, because we're dealing with the mean, okay? And come down, so first the mu, 16.1, our original mu, our x bar, so our mean of the sample, 15, our standard deviation of the sample, 25, our number in our sample, 49, and we want it to not be equal to the original one, that is our alternative hypothesis, and we just do calculate, okay? And you find your t-score to be negative 0.308, which is part D right here, okay? You do have to do the standard deviation by hand. It doesn't come up in this t-test, even though you technically don't need it now to find the t-score. I think they just want to make sure that you can find that. But both the t-score and the p-value, right, are here. The p is 0.7594. So now we do not reject the original hypothesis because our p-score is not less than our significant level, okay? Because the p-score is not less than the significant level, we are not going to reject the hypothesis. Okay, and our last one. So same thing, but this time we're just using a proportion, which is what you do with your qualitative data for your project if you're doing it. According to the US Census Bureau, 7.1% of Americans living in 2004 are young adults. Okay, so that's our proportion here. Suppose that a random sample of 400 Americans was selected. That's our N and our X value, and contains 35 young adults. Okay, so our original hypothesis is that the proportion of young adults is 7.1 versus our alternative hypothesis, which is test whether the current proportion of young adults is different. Okay, so it's just as different, not less than or equal than, is different from the 2004 proportion. So the alternative hypothesis is that it is not equal to that. State the sample proportion p hat and the standard deviation of the sample proportion. So p hat is going to be 35 over 400. And our standard deviation of the sample proportion, same equation that we've been using, is going to be 0.0128. Okay, perform the z-test, which can also be done on the calculator, same as we just did, but you do z-test instead of t-test. And it'll give you, this is your z-score, and then this is your probability. So since your probability is not less than your significance, okay, we do not reject the original hypothesis. Okay. All right, and that is it If you have any more questions, please reach out to me. We will be taking the test tomorrow at 10 a.m. Your projects are due today and test tomorrow. And if I stay up all night grading, you should have a grade early Friday morning. Hopefully I'll see you guys at the parade.